Hey guys, okay. Second part 2, which was a good little break because we finished that first section for 13.1. So now we're looking on page 454, and it's determining the enthalpy of chemical reactions using bond energy. Now, if you need to stop right here and go back and make sure that you know how to do bonds. Remember Module 4 when we talked about how you write out those Lewis structures? That's what we're doing in this little section. Remember when I said, you're not going to have to do this till the end of the year, and then everybody was like, oh, that seems so far away, and then all of a sudden here it is. So this is the module that we use Lewis structures for this one little thing. I think you have one question on your test that has to do with it, and it's kind of easy, but you still need to know what we're doing here, so let's do this together. 454, first section of the paragraph. When a chemical reaction occurs, the valence electrons of that atoms that make up the reactants must rearrange themselves into configurations necessary to make products. Now, this is all going to make sense in just a second. The process requires a lot of chemical bond breaking and chemical bond making. Okay, now, when we had our chemical reaction, our chemical equation here on the board, and it's balanced, you know that if we have this on the reactant side, it has to mix up, change up to go on the product side. And that's what's produced from the mix up, change up. That's what this is. It's the mix up, change up. So what we're doing is it's saying you got to break the bonds that are on the reactant side and form new bonds on the product side. And it has to match up. That's why we have balanced equations. So look on page 455. This is CH4 plus 2 oxygens turned into CO2 and H2O. This is the same reaction that we did just a few minutes ago. Now, the Lewis structure is written in this way. You have your carbon that has 4 valence electrons, and then your hydrogen that bonds with each of them. That's why it's CH4, 4 hydrogen, 1 carbon, okay? Same with our oxygen. Remember, the oxygen has, watch me say 6. Yes, yes. 6. It has 6 valence electrons, and we have O2, which is 2, and we have 2 O2s. So that's going to be 2 double bonds, okay? Then on the reactant side, we already have our answer that it's CO2. You've got 2 double bonds there, and then the H2O. Look how the H2O is in a bent reaction, the H2O. Looking at the equation in this form, we can see that there are reactants to turn into products, and several bonds have to be broken. The reason that we break one, it takes a lot of energy to break those bonds and start new bonds on the product side. Look on the third paragraph down, 455. Takes energy to break those bonds. As the bonds on the reactant side of the equation are being broken, energy is being absorbed by the reactants. Absorbed equals endothermic equals positive. Each time a bond forms on the product side, energy is released. And when that energy is released, that is an exothermic negative reaction. Okay, next to last paragraph, 455. Suppose a chemical reaction involves reactants with very strong bonds and products with weak bonds. Since the reactant bonds are strong, it takes a lot of energy to break them. So the reactants tend to absorb a lot of energy. On the product side of the reaction, the bonds are weak. This means that they are formed. The product released only a small amount of energy. In this situation, the reactant has to absorb a lot of energy, and the product only releases a little. On balance, the chemical reaction absorbed more energy than it released. This reaction would be considered endothermic. 456. And let's finish off that bottom paragraph. On the other hand, consider a chemical reaction in which the reactants contain weak bonds and the product contains strong ones. In this situation, the reactants would not need to absorb much energy because their bonds would be easy to break. On the other hand, when strong bonds are formed, a lot of energy is released. Therefore, the chemical reaction is going to be absorbed, and it's going to be it's going to be absorbed, making the reaction off balance, and it's going to be an exothermic reaction. One thing that you need to see from this discussion is that whether a reaction is exothermic or endothermic, energy is going to be on both sides. It's going to be absorbed and released in this reaction. The difference between endothermic and exothermic depends on how much energy is absorbed and how much is released. If it's going to be more in the reactant side, it's endothermic. If it's going to release more, it's exothermic. Okay, now, these are called bond energies. It's the measure of strength that it takes to break these bonds, and that's called specific bond energies. So, bond energies are the amount of energy stored in a bond between the atoms and the molecules. Okay? On page 456, you have a table of standard bond energies. This gives them to you. You're going to need this table, so you can refer to it. Let's look and see. It is on page 610, and you can use that for your test. You're also going to need all of 610 for this module and the test. You're going to need all of these tables, so go ahead and put a little piece of paper in it and mark it because you're going to need it. These are measured in kilojoules per mole. Remember, you're going to have some moles here, and that means you're going to have to know how to use stoichiometry. Look at the bottom part of page 456. Suppose that you had 1 mole of chlorine molecules. We would write the Lewis structure of chlorine to find out that the 2 chlorine atoms that make up the molecule are held together with 1 chlorine to chlorine single bond. Now, chlorine, if I look it up on my periodic table, is a 7 valence electron. So I've got my chlorine here, and it's got 7 valence electrons. 2, 4, 5, 6, 7. Okay? So I've got 2 of them. So I'm going to just write another one right up here. 1, 2, 3, 4. Remember, you start on the 3 o'clock. So 5, 6, 7. And then that's going to make a connecting bond right here because I'm missing this valence electron. Since there's 7, I've got 1 here and 1 here. Bring them together. That makes a single chlorine bond. Okay? Now, where was I? 2 things. First, if you wanted to break apart 1 mole of chlorine molecules, you'd have to expend 240 kilojoules of energy. How do I know that? Because look at this little table right up above it. Cl to Cl with 1 single bond is 240 kilojoules per mole. 2 seconds. My nose is a-dripping. Okay, so I have my single bond chlorine, 240 kilojoules per mole. But how many moles is it? We already said that I had 2 of them, remember? So that's going to be 2 moles. Let's see. So that would be written when we're writing out these problems we're getting ready to do next. This is how you're going to write them. You're going to write 2 times 240 kilojoules per mole. Okay? That's how you're going to do it because up here, remember, it was Cl2, but there was 2. So the 2 is going to carry down. Now, where'd my eraser go? We'll get to all that in just a second. Table's going to be available for your test. Okay, page 453. Before we see how bond energies can be applied to learn about the energetics of a chemical reaction, we want to point out that you needn't memorize anything on 13.2 because that's just crazy. Who in the world would want to do that? I don't want to do it. You don't want to do it. Don't do it. No chemist has all these memorized. Well, I'm sure there's somebody that has memorized. There's somebody out there that really thinks this is important, but in my life it's not, so we're not doing it. So throughout the rest of the module, 7 more tables will be presented. You're going to have all of them on page 610, like I just told you. All the tables you need to solve the problems, blah, 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 blah. Go to page 610. Now that we have the table for bond energies, how do we use it to analyze the energetics of a chemical reaction? To determine whether or not a chemical equation is endo or exothermic, all we have to do is figure out how much energy is needed to break. Remember, a few minutes ago, we were given that amount. We were given the negative and the positive numbers. One was like 800 and something, negative 800 and something, and another one was positive 517, okay? That told us what we're looking for here, okay? Now, here's a formula, an equation that you're going to need. It's in the middle of page 457. I'll go ahead. I haven't done it yet. I'll send you, when I send you your Module 13 test, I will add all these equations on there so that you'll be able to use them because you'll need it. So, enthalpy mathematically is written. Enthalpy equals energy required to break the bonds minus energy released when bonds form. The table of bond energies gives us this information. To do this, you need to be able to look at the equation in terms of a Lewis structure because you got to know how many bonds you've gotten. You can't just look at it and guess how many bonds you have. You have to write out that Lewis structure. That's the only way that we're going to know what kind of bonds are broken and what kinds are formed. So if you got to go back now and review Module 4, get to it before you do any more. So stop the tape, do whatever you need to do, and review Module 4. Suppose the energy absorbed to break bonds is greater than the energy released. In this case, the chemical reaction will be endothermic. What sign will enthalpy have? Well, if it's endothermic, what sign is it going to have? Positive. On the other hand, if it's exothermic, the energy absorbed to break it down is going to be less than the energy released. So the answer from equation 13.2 will result in a positive or a negative number. And when we get that number, you'll see if it's going to be endo or exothermic. Now, let's do example 13.2. All right. This is the, hang on just a second. I wrote 13.2 down and I want to go over it. But sadly, I cannot remember where I wrote it down. Sometimes I make notes a little bit of everywhere. Sometimes I put my finger in places and can't remember what I'm doing. Okay. Well, I can't find it. I'm a goob. Which is fine. We'll just work it out together. Y'all love it when I do that, because then you see that sometimes I'm just as lost as you are. Okay, let's see. To make ammonia, we're on page 457. To make ammonia, nitrogen and hydrogen are reacted at high temperatures according to this equation. Let's go ahead and write the equation down. N2 plus 3H2, is that what it says? Equals 2 N NH3. Remember that NH3 is ammonia. So to make ammonia, we are given this equation. So we're given our balanced equation. Then, what is the enthalpy? We're looking for the enthalpy. And is it endothermic or exo? Endo or exo. All right, now we have to do some Lewis structures. I know y'all are so excited about that because I am too. Okay. Nitrogen. Okay, if you look on your periodic table, you're going to see that nitrogen has 5 valence electrons. So I have 2 nitrogen, and I'm going to go nitrogen. Okay, now I got Spider-Man all up in my head, and I can't quit thinking the song. 1, 2, 3, 4, 5. And then on this one, I've got 1, 2, 3, 4. That's not going to work. 5. Okay. I'll do that. Absolutely correct. So now it looks like I can share this one and this one, this one and this one, this one and this one. That's going to look like, when I write it out, it's going to look like, I'm going to erase that. Triple bonds, my nitrogen triple bonds, okay? Then I have hydrogens. Well, I've got 3 hydrogens, H2s. So my hydrogens, you know, we're going to single bond. Okay, so right here, I'll do that in a second, never mind. Okay, then I'm going to do my 2 NH3s. Now, I've got my nitrogen, which has 1, 2, 3, 4, 5. Hey, let's do it right. Trying to go ahead and line it up, but that's just not going to work. Okay, so I've got my nitrogen, and now it says I have 3 hydrogen. H, H, H. Single bonds, same thing here. H, 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 because I have 2 of these, okay? So now I have to count my bonds. Now I'm going to do that with a pretty, no, that's not bright enough. Let's use a red pen, okay? So for my nitrogen, even though this is a triple bond, it's just 1 bond. So I'm going to put a 1 right here. I've got 1, 2, 3 bonds right here. 1, 2, 3, 4, 5, 6 bonds here. Remember, this is NH3. This is 1 molecule. Now's where my tables come in handy dandy. Remember how before I did some little math problems there? I'm going to look first at my nitrogen. My nitrogen is 1 times, if I look up nitrogen over here on page 456, sorry, it's going to be 942 times 942 kilojoules per mole. Okay, plus 3 hydrogen and hydrogens are 432. So it's 3 times 432 kilojoules per mole. Produces, minus 6 of my NH3. Look on the next page. My NH3 is 386 kilojoules per mole. Okay, now this comes straight off the formula that is on page 457, equation 13.2. Okay, so now I'm going to pull out my handy dandy calculator. And I've got 942, wait a minute, 3 times 432 equals 1296. 6 times 386, 2316, and then this one's going to be 942. So 942 minus plus 1296 minus 2316 equals negative 78 kilojoules. And this is negative, so we're looking to see, is it endothermic or exothermic? Exothermic. So negative 78 kilojoules is exothermic. In the next practice problem there, you're going to be able to see that it's a little bit more drawn out. It is a combustion problem, so that means you're going to have to add oxygen to your reactant side. You're going to have a carbon dioxide and water on the product. You will have that, okay? So when it asks you for the enthalpy, and it asks you if it's endothermic or exothermic, the 13.2 is what you're going to use. Now, we're going to talk a little bit about Hess's law. Even at home, I can't find my eraser. Okay, ready? I used to couldn't do that because for a long time I took Botox for my migraines, and I had 51 shots. I took them every 3 months, and they went all across my head, like down through here, down the back, through my neck, and in my back, and 51 shots every 3 months, and it hurt. But so they gave me the Botox up here, so it's kind of like having that cosmetic stuff. I mean, because my eyebrows didn't move. But, I mean, if y'all tried to look terrified, it was like, ah! If I looked happy, it was like, I mean, it was, couldn't move my eyebrows. And y'all know I'm very expressive with my face. So can you imagine me not being able to move my eyebrows? It's kind of terrifying. So anyway, I don't take it anymore. I had a reaction to it, and it made this side droopy. See, it's weird, isn't it? So anyway, it made this side a little droopy. So we had to stop because I don't want to, that would be me. I'm sure that would be me. So Hess's law. Okay, here we go. Okay, I thought this was kind of funny. On page 460, at the bottom of the page, last part of that first paragraph where it talks about Hess's law, it says, a complete discussion of the topic, it is necessary to provide you with all this information. And your ability in chemistry will determine how much of this information you can actually absorb. So what it's saying is, if you are really chemistry minded, you're just going to go pow pow, and this is going to come together. But if you're not chemistry minded, sorry. That's what I thought. That was kind of mean thing to say to somebody. Kind of blow your hopes right there before you ever get started. I think I'm the one who doesn't absorb chemistry as much. But here I am. So let's get stuck together. Okay, so Hess's law. Hess's law is enthalpy in a state function. Now that does not mean that, a dinner party, like a state function that you've got to go to. That's not what that means. State function is any quantity that depends solely on the final destination, not how you get there back and forth. So let's say that my friend Melanie, she lives in Alabama, and she's going to go to Dollywood, and I'm going to go to Dollywood. So she comes from Alabama, and I come from Knoxville. We're going to meet in Dollywood and have us a good old time. Once we get to Dollywood, even though we took 2 different routes there, we got there 2 different ways, we still had the same amount of fun at the Dollywood, right? So, me and Melanie would have a blast at Dollywood. I love my Melanie. So, the state function is the fun that we had, because that's the important part. That's the work that was done here, okay? How we got there doesn't matter. The fun that we had while we're there, that is state function. So, how does that work in something like this? Let me find that answer. Hess's law tells us that enthalpy is a state function. That's what Hess's law says, that enthalpy is the final outcome, okay? The state function. Hess's law just a minute. I'm sorry, I thought I heard somebody out there with my youngins. I was gonna go get me somebody, but there wasn't. Okay, so let me find that again. Hess's law tells us that enthalpy is the state function. In other words, the amount of energy contained in a substance independent of how it's made. For example, each of the chemical equations below is a way of making water. Okay, if all we care about is getting water, then you can do this. You can have a chemical reaction. 2H2O plus O2 equals 2H2O2. We have water. Or you can take hydrogen peroxide and decompose it. And if you decompose it, it's H2O plus O2. So even though we also got some oxygen with it, the goal was water. My kids are outside chasing each other with a glass of water. They've been fighting bees all day because the carbon debris are out. So they're out there whipping each other with a glass of water. So they probably deserve it. So whoever wins, you know, I guess. So anyway, how does that help us calculate the enthalpy in a chemical reaction? Remember that the delta H remembers the change of enthalpy. So it's the change of enthalpy that occurs in that chemical reaction. It's like it somehow knows the enthalpy inside of that reaction. I don't even know how to explain it. Let me just read it. How does that help us calculate, knowing that it's part of a state function, that the Hess's law is that enthalpy is a state function? How does that help us calculate it? It represents the change in enthalpy that occurs within the chemical reaction. If we somehow knew the enthalpy of each substance in the chemical reaction, we would simply take the difference of the enthalpies of the products and the enthalpies of the reactants to get the enthalpy of the reaction. So it's saying that if you take the enthalpy of the product and that of the reaction and subtract them, then that gives you the enthalpy of the entire equation, okay? Let's look at page 462. It is very hard to actually measure the enthalpy of the individual substance. The only thing that chemists can measure in a chemical My kids are coming in. It distracted me. The only thing that chemists can measure is the change in enthalpy that occurs in the chemical reaction. So we have what is called enthalpy of formation. And I'm going to erase this part right here and give you another. Let me do that. That is the enthalpy formation, okay? It's on page 462. It is the enthalpy of a formation reaction. Now, the formation reaction, remember, has the independent elements on this side, and then we're going to bring them together. We're going to form something out of it, okay? So, right below that, the enthalpy of formation of any given substance is just like the enthalpy of formation reaction that creates the substance. Remember, you're not going to change it's not going to, you're not going to start over here with B's and end up with oranges, right? It's all going to come from the same thing. You're going to use these to form this, but the elements are going to be the same, just in complete molecules. So, having the enthalpy of formation of a substance is equivalent to having the enthalpy of that substance. So guess what? We have a whole table of the standard enthalpies of of the formation. So it gives us those here, okay? That's going to help us a whole lot. So let's look. Having that is equal to having the enthalpy of that substance. Now, we're going to add a little bit to that. Most chemistry is done at room temperature. Remember that room temperature averages 25 degrees Celsius and normal atmospheric pressure, which is 1 atm. We call these standard conditions. To indicate that something is under standard condition, it includes a degree symbol, and we call those the standard enthalpies of formation. Enthalpy formation, if we add the degree symbol, it's going to give us the standard enthalpy formation at standard conditions. And that is what table 13.3 is. Okay, so notice that it says substance, like your first substance there is water. It is negative 242. That is the standard at 1 atm at room temperature. That is the standard enthalpy of formation. Okay, now let's see. The next step you'll see is over on page 463, and boys and girls, we're almost done. So that is on page 463. I'm going to give you this equation as well. Do not get this equation mixed up with the other ones, okay? Don't get this one mixed up with the other, 13.2? Don't get it mixed up. I'm going to write on your paper exactly what it is, all the little marks, the differences between this and this and this, okay? I want you to know these differences so that you don't work some other problem when you should be working this one, okay? So, here's this weird equation. Now, as you may know from algebra, which most of you should have finished, the E looking symbol stands for summation. Now, that means it's the sum of whatever is in the product or the reactant. So, pardon me, my windows are open, my allergies are getting me. Equals, I don't do the formation, it's just standard enthalpy. Okay, so I'm looking for it. Hang on. No, that's right. The book's missing my little F. Okay. The book is missing my little F there in my book. And so you can figure that out. Okay. We're looking at the sum of standard enthalpy of the product, okay, minus the sum of the standard formative enthalpy for the reactant. Product is over here this time. This can throw you off. You need to remember that in this equation, in 13.3 equation, product's going to be on this side because it's got to subtract the reactants. It's going to give us a positive or a negative, and that positive or a negative is going to be an endothermic or an exothermic reaction. Okay? So, also note, the standard enthalpy of formation of an element in its elemental form, talk about that in a second, is 0. That includes all of these elements on page 463, all of these elements right here. They are calcium, sodium, potassium, iron. They all have an enthalpy of 0, the enthalpy formation standard of 0. It also includes the homonuclear diatomics, HNOCl. Same thing, 0. Okay? You're going to have to remember that. I'm not writing that down anywhere. You're going to just have to, off the top of your head. Let's look at the following reaction. 2NO plus O2 forms 2NO2. Now, we have to look up a few things. I just totally lost my place. So, this is my given, okay? I have to find, is it exo or endo? So my plan is to work 13.3. So here's what I have to do first. Standard enthalpies on page 462. What have I got? NO. That is, sorry. I totally lost my train of thought. I've got to go back. I'm not going to start with NO. That's where I threw myself off. Okay. I'm going to start with my product. Your product goes first. My product is first here in this equation. So my product is NO2. That's where I threw myself off a second ago. I said it out loud and thought, what am I saying? NO2 is 33.2. So I have equals 2 moles times 33.2 kilojoules per mole. Plus, this should go straight on. If I had my big board, this would be super easy, okay? This is definitely something you don't want to watch on your phone because you won't be able to see this on a little phone. Then I have the second part of my equation. This is what's in my product. So now I'm going to subtract what's over here. So I have 2 moles of NO on page 462, 2 moles of NO times 90.3 kilojoules per mole. And what did I say about this? Plus 0. Okay, it's going to be 0. This is in its elemental form, and anything that's singularly in its elemental form is going to be 0. So 2 times 33 is 66.4. I'm going to cross out my moles. And 2 times 90.3 is 180.6. Cross out my moles. So it's going to be delta HF standard equals 66.4 kilojoules minus 180.6 kilojoules. Handy dandy calculator. (66.4) minus 180.6 equals negative 114.2 kilojoules. Now, is this positive or negative? It's negative. Does that make it endothermic or exothermic? It is exothermic. It's exothermic, and we know that it's exothermic because of that negative symbol, and that tells us that it puts off heat. It releases a higher amount of energy than it in the product than it does in the reaction. Okay, so let's see. Is there anything else on here? Nope, that's it. That's it for this week. So you're going to have 2 videos apparently, because when I paused it to cook some lunch for my husband, I accidentally stopped it. So now you got 2 videos. So make sure you watch the other one first. It's about 26 minutes. This one's about 42. The next video that I shoot will be the second part of this module, and it'll be next week. You'll be sent this video on probably Sunday night, the 29th. You'll be sent this video Sunday night, the 29th, and so you'll be ready to watch it on Monday or whenever you choose to watch it. Take notes, do the practice problems, do the on your owns, and then be ready for the next Monday, which is April the April the 6th. Be ready on April the 6th to get the second part of this module. When I send you the video, I will send you the copy, the file for your test. I'll include all of these equations that you need, but you're going to have to look in the back of your book. I'm not typing out all of those tables. I'm not going to do it, so you're going to have to look on page 610 for that during your test, and that is perfectly fine. They tell you to do that. So if you have any questions, you can text me or email me. I'm not going anywhere right now. We're staying hunkered down and obeying the law, and we are trying to stay healthy. I've told you all before, if you've heard my testimony, you know that I have a paralyzed vocal cord, and I have an autoimmune disorder that causes me to catch stuff. So I tend to catch things, and especially if I'm flaring up in the autoimmune, I tend to get stuff. And with an airway obstruction of 40%, that increases any issues that I might have with anything respiratory. So please continue to pray for me and my family, because if I'm not here, I think my family would absolutely die. So they would all starve to death, that is for sure. So if you will please pray for me, pray for each other, pray for Governor Lee, our Knox County Health Department. Pray for Donald Trump, who is really he really is, I think he's trying to work hard on this. Pray for Dr. Fauci. He is fantastic. He's brilliant. And he's the one that is coming up with a lot of these rules and regulations, that he is on the task force with Vice President Pence and a host of other physicians. Pray for their wisdom and discernment as they're making decisions. It's got to be hard. I'm glad that's not my job. It's hard enough to get on here and shoot a video, because that is my job. So it's hard enough for me to do this. So I would hate to be in their shoes. Pray for them. Pray for me. Pray for each other. And you will see me back next week on this video. I love all of y'all. Bye.